оценки. Я группе обещаю, что я проверю их мидтермы уже типа недели полторы и не проверяю. А мидтермов много. Причем я в одной группе проверил полностью в первый же день, а во второй не проверяю и всячески откашиваю от этого.
Думаешь, расстроит?
А? Они хотят знать оценки. Тем более, что у них все оценки, в общем, и так плохие, за мидтерм, скорее всего, тоже плохие. В общем, их очень интересуют их оценки.
Ну ладно, не очень понятно. Записывает нас или нет? А, понятно, только под названием Амбург НЯ геометрия 1. Ну ладно, пусть Гош потом сам разбирается. Так, почему?
О, я не опознал даже. Ох.
Okay, so let's continue our discussion of topological tensor products. At the end of the previous lecture, we explicitly described the projective tensor product of some concrete bounded spaces. So our main example was the tensor product of two little one spaces. So let's recall that if we have two little one spaces, L1I and L1J, then we proved that their complete projective tensor product is isometrically isomorphic to the little one space on the product of I and J. And this isomorphism is uniquely determined by the following rule. It takes each elementary tensor of the following form, EI tensor EJ, to EIJ. Where EI is roughly a sequence whose ith element is 1 and it is 0 elsewhere. So formally it's given by the following formula. The J component of EI is just the Kronecker delta. So let's call it proposition 1. And this result can be generalized in several ways. For example, this was an exercise. For example, we can replace here one of the L1 spaces by an arbitrary bound space. And it turns out that if we take the projective tensor product of L1 of I and an arbitrary bounded space, then what we get is the vector valued L1 space, which consists of all absolutely summable families in E, indexed by I. Another generalization of proposition 1 was about the big L1 spaces. You have two big L1 spaces on measure spaces x mu and y mu. Then their complete projective tensor product turns out to be isometrically isomorphic to 1 on the product x and y. And the isomorphism takes every elementary tensor f tensor g to the function h, given by the following simple formula. And this isomorphism is uniquely determined by this rule. Proposition 1 also has a useful locally convex generalization. And to discuss this generalization, we introduced, at the end of the previous lecture, we introduced the so-called Kyoto spaces. Kyoto spaces. So let's recall the definition of a Kyoto space. We start with a set P, which consists of non-negative real valued functions on I. So I is an arbitrary set. In many concrete examples, I is countable. Sometimes it's convenient to take the set of natural numbers. Sometimes we take the set of integers or z to the power n. But in most interesting examples, I is countable. So we may think of elements of P as sequences indexed by I. We assume that P satisfies some natural conditions condition 1 was that for every I, there is an element in P such that Pi is strictly positive. And condition 2 was that this set P is directed in the sense that for any two sequences P and Q from P, there exists a constant C, there is another sequence R in P, such that the maximum of Pi and Qi is dominated by Ri in the following sense. So if these conditions are satisfied, then we say that P is equal to set. P is equal to set if conditions 1 and 2 are satisfied. And given the Curtis set P, we define the so-called Curtis space. Curtis space as follows. It is denoted by lambda 1 of IP, and it consists of all sequences, or more probably elements in the space, that is functions from I to K, such that for every little p, for every sequence little p from our Curtis set, the pointwise product of x and p sits in L1. So formally this means that the following sum is finite for every little p in our Curtis set. So it's this set is seen to be a vector subspace of k to the power I, and moreover it's a complete locally convex space for the topology generated by all seminorms of this form. So the seminorms are indexed by sequences from our Curtis set. We discussed some concrete examples of Curtis spaces. Let me briefly recall that. Let me briefly recall some special cases. Of course, the little one space is a special case of a Curtis space. So in this case, the Curtis set P consists of a single sequence, all of whose elements are identically 1. The space of all k-valued functions on I is also a Curtis space. To see this, we take for P the set of all functions with values in 0 and 1, such that all but finitely many elements are 0. The space little s of rapidly decreasing sequences is also a special case of Curtis spaces. And more generally, the space little s of z to the power n, which consists of rapidly decreasing sequences indexed by n tuples of integers, is also a Curtis space. The space of holomorphic functions on the complex plane is also topologically isomorphic to a suitable Curtis space. And more generally, the space of holomorphic functions on an arbitrary n-dimensional open n-dimensional polydisk is also isomorphic to a suitable Curtis space. And this list of special cases can be extended. So morally, Curtis spaces are everywhere. In fact, Curtis spaces, there are at least three reasons why Curtis spaces are important. First of all, they are important because they are everywhere. So many classical spaces of functional analysis are isomorphic to Curtis spaces. So in particular, one can prove that the Schwarz space is isomorphic to a suitable Curtis space. More exactly, it is isomorphic to little s. The space of smooth functions on an arbitrary smooth manifold is also isomorphic to a suitable Curtis space. The space of holomorphic functions, spaces of holomorphic functions on many classical domains and on many classical manifolds are also isomorphic to Curtis spaces, and so on. So there are many concrete examples of Curtis spaces. The second reason why Curtis spaces are useful is that they are very concrete and handy. So in some sense, we can easily do concrete calculations with Curtis spaces. And the third reason is that Curtis spaces are often used as a source of various counterexamples in the theory of topological vector spaces. Okay, so what we're going to do now is to describe the projective tensor product of two Curtis spaces. So let's introduce some notation. Suppose we have two Curtis sets, P and Q. So P is a Curtis set on an index set I, and Q is a Curtis set on another index set J. Curtis sets. We construct a new Curtis set, which will be denoted like this, P circle Q. This will be Curtis set on the product of I and J. And this set consists of all functions of the following form. We take all functions little p from P and little q from Q and form pointwise products of their entries, Pi and Qj. Here P runs over big P and Q runs over Q. So this is equal to set. Equal to set on the product I times J. A claim, this is proposition. Oops. Where was the previous page? This is only proposition 3. There exists a topological isomorphism between the projective tensor product of the Curtis spaces lambda 1 of IP and lambda 1 of JQ and the Curtis space of I times J corresponding to the Curtis set P circle Q. And it is defined in exactly the same way as for the little one spaces, namely by the following formula. The proof of this result is a slight modification of the proof for the little one spaces. So I'll leave this as an exercise for you. This is very similar to the proof of proposition 1. The arrow from the left to right arrow is constructed by the universal property of the projective tensor product, so we simply linearize the suitable bilinear map. And the right to left arrow is constructed as a sum of a suitable series which converges absolutely, and the absolute convergence follows from the definition of the Curtis space. Okay, so why is it useful? This result is useful because it has numerous interesting corollaries. Corollary 1. There exists a topological isomorphism between the projective tensor product of the space of smooth functions on the m-dimensional torus and the space of smooth function on another torus of dimension n, and the space of smooth functions on their product, that is, on the torus of dimension m plus n. And this isomorphism is uniquely determined by the following formula. It takes every elementary tensor f tensor G to the function h, where h is given by the following formula. This result can be deduced from proposition 3 as follows. Well, it's sketch of proof, but I hope you will easily reconstruct all the details. So let's look at the space little s on z to the power n, the space of rapidly decreasing sequences indexed by z to the power n, and try to form the tensor product with a similar space on, so let it be z to the power m, and here we have z to the power n. If we substitute these concrete Curtis spaces here, what we get is exactly little s on z to the power n, m plus n. This follows from proposition 3. On the other hand, we have the Fourier transform, which gives us a topological isomorphism between C infinity on the torus and the space of rapidly decreasing sequences in this way. And similarly, we have here C infinity on the m-dimensional torus and C infinity on the n-dimensional torus. Again, this is just the tensor product of two Fourier transforms. So we go now from here to here, then we apply this isomorphism and then the inverse Fourier transform. So as a result, we get an isomorphism between these two spaces, and a straightforward calculation shows that the resulting isomorphism here is the isomorphism given by this formula. And that's it. In fact, we will see soon that this result can be extended to spaces of smooth functions on arbitrary smooth manifolds. But this is not that immediate. We'll need some theory of nuclear spaces to go to that. Corollary 2 is about spaces of holomorphic functions on polydisks. There exists a topological isomorphism between tensor product of the spaces of holomorphic functions on the m-dimensional polydisk of polyradius R and the space of smooth function of holomorphic functions on another polydisk of dimension n, and say of polyradius S. So this topology, this projective tensor product turns out to be isomorphic to the space of holomorphic functions on the polydisk of dimension m plus n and of polyradius RS. And this isomorphism is given by the same formula. It takes every elementary tensor, f tensor G, to the function h, given by the following formula. And the proof is similar to the proof of corollary 1. So you take suitable Curtis spaces, which were discussed in the previous lecture and which are isomorphic to the respective spaces in this formula, to the spaces of holomorphic functions on the polydisk, and apply proposition 3. And again, this result actually extends to arbitrary complex analytic manifolds. By the way, also I'd like to stress that actually in these formulas we can replace the projective tensor product by the injective tensor product. This is not entirely obvious, but this will follow from the nuclearity of the spaces, which will be discussed at the end of our course. For L1 spaces, this is not true. So if we look at previous results, we look here, then in general, we cannot replace here and here the projective tensor product by the injective tensor product. So the projective tensor product in the framework of balanced spaces, the projective tensor product is adapted to L1 spaces, but the injective tensor product is adapted to another kind of spaces, which we are now going to discuss. So now, let's now discuss some examples in which the injective tensor product behaves much better than the projective tensor product. Let's start with the following definition. Suppose that E is a semi-normed space. We say that a set S, which is contained in the closed unit ball of the dual space E prime, we say that S is norming if for every x in E, the norm, or more exactly, the semi-norm of x is equal to the following number, the supremum of f of x, where f runs over s. Let's look at some concrete examples of norming sets. Of course, the first obvious example is the unit ball itself. This is a norming set, which is immediate from the Banach theorem. Also, it's more or less clear that that an arbitrary dense subset of the unit ball is also norming. Any dense subset of the unit ball. Example 3. Suppose that E is the space of continuous functions on a compact topological space X. And for every point, little x, let's consider the variation functional at this point. The variation functional which takes every function f to f of x. Then it's clear that if we consider all such functionals, then they form a norming set over all x in X. So this is a norming set, just by the definition of the supremum norm of a function. Okay, so why do we need norming sets? We have the following lemma. Suppose we have two semi-norm spaces, E and F. And suppose that we have two norming sets, S and T. S is a norming set for E, and T is a norming set for F. I claim that the injective tensor semi-norm can be calculated by using S and T in the following sense. For every element U in the tensor product, the injective tensor semi-norm of U is the supremum of the following numbers, F tensor G applied to U, where F runs over S and G runs over T. In other words, if we recall now the definition of the injective tensor semi-norm, in the definition, F runs over the unit ball of prime, and G runs over the unit ball of F prime. So the point of the lemma is that we can replace, in the definition of the injective tensor product of the injective tensor semi-norm, we can replace the unit balls by arbitrary norming sets, and the result will be the same. To prove the lemma, let's introduce some pure algebraic notation. Suppose that E and F are just vector spaces. And suppose we have two linear functionals. F is a linear functional on E, and G is a linear function on F. So we can now consider the following map. F tensor 1, where 1 denotes just the identity map of F. So it acts from E tensor F to the tensor product of K and F, where K is our base field. But of course, this tensor product is canonically isomorphic to F. So the composite mapping will also be denoted by F tensor 1. Usually this doesn't need any confusion. Similarly, we may consider the tensor product of 1 and G, the identity map of E, tensor G, which acts from E tensor F to E tensor K. But again, E tensor K is canonically isomorphic to E, so we may look at this map as a map from E tensor F to E. And this map will be denoted by the same symbol 1 tensor G. And let's also observe that if we use this notation, then we get the following identities. The tensor product of F and G, which is by our convention a linear function on E tensor F, can be decomposed in the following way. It is F composed with 1 tensor G, and on the other hand, this is G composed with F tensor 1. To prove these formulas, we simply substitute elementary tensors. So these functionals agree on elementary tensors, and since every element of the tensor product is a sum of finitely made elementary tensors, we get these equalities. Well, look, 1 tensor G acts from here. F tensor 1 acts from here to here. G acts from F to K. So this is well defined. Okay, so now let's prove our lemma. So by definition, the injective tensor seminorm of U is the following supremum. Now let's write it as the iterated supremum over the unit balls. Of F tensor G applied to U. Now we replace this expression by this one. So we keep the supremum over the unit ball here. And we write this as F applied to 1 tensor G of U. So now what is this? Well, this is the supremum over unit ball of a linear functional applied to a fixed element. So this is nothing but the norm of this element. This is the norm of 1 tensor G of U. So we now use the assumption that S is norm in set, and so we can replace here the unit ball by S. So this will be the supremum over the unit ball. In the second supremum, we replace the unit ball by S. And we write the same element. Okay, now we interchange the supremum. Supremum over S, supremum over the unit ball. So G runs over the unit ball. And now we we write this element in an equivalent way, namely this way. This is G applied to F tensor 1 of U. And again, what is this? This is nothing but the norm of F tensor 1 applied to U. So we now use the assumption that T is a norm in set, and so we can replace here the unit ball by T. Supremum over T. And this is nothing but F tensor G applied to U. And that's it. So this gives us the required form. Okay. Let's now apply our lemma to some concrete cases. Proposition 4. No mistake. Proposition 4. Suppose that we have two compact Hausdorff topological spaces, X and Y. Compact Hausdorff topological spaces. Then there exists an isometric isomorphism. Between the complete injective tensor product of C of X and C of Y, and the space of continuous functions of X cross Y. And this isomorphism is uniquely determined by the same old formula. It takes every elementary tensor of the form F tensor G to the function H, given by the following formula. H of xy is F of x, G of y. Again, it's essential here that we take the injective tensor product. For the projective tensor product, the result fails. To prove this result, let's first start with the pure algebraic situation. So we consider the bilinear map from C of x cross C of y to C continuous functions on the product, as denoted by phi, where phi is given by the following formula. Phi of fg is the function of the product given by the following formula. So clearly phi is bilinear, so we can linearize it through the algebraic tensor product. Little phi is the linearization of big phi. And let's now observe that little phi is also given by the following concrete formula. Phi of u is the function given by the following formula. So this function evaluated at x and y is the following functional applied to u. Well, indeed, okay, this is true if u is an elementary tensor in here by the commutativity of the diagram. And since this is true for the elementary tensors, by linearity, this is true for all elements in the algebraic tensor product. So now we calculate the norm of phi of u. The supremum norm of phi of u is just the supremum of this expression over all x and y. And now we just apply our lemma. So these evaluation functionals run over normal sets for C of x and C of y spaces. So by lemma, this is equal to the injective tensor norm of U for every U. So we see that little phi is in isometry. It is an isometry if we equip the injective tensor product with the tensor product with the injective tensor norm. Isometry with respect to the injective tensor norm. On the other hand, if we apply the Stolz-Weierstrass theorem, we see that the map phi has dense range. Oh, indeed, the range of phi is a subalgebra in C of x cross y, which separates the points, and it's self-adjoint. It goes down the conjugation. So it satisfies the conditions of the Stolz-Weierstrass theorem, so little phi has dense range. And so it uniquely extends by continuity to an isometric isomorphism. Extends to an isometric isomorphism between the completion of the space, which is just the complete injective tensor product, and C of x cross y. And that's it. This is our isomorphism. This result can also be generalized in several ways. For example, exercise for you. Suppose that E is a bound space, and as before, X is a compact Hausdorff topological space. Construct an isometric isomorphism between the injective tensor product, the complete injective tensor product of C of x and E, and the space of continuous E-valued functions on X. The only point here in this exercise, which is harder than in the proof of our previous proposition, is the density of the range. Here we cannot apply the Stolz-Weierstrass theorem, so the density of the range of the respective map is proved by using suitable partitions of unity. But this is not very hard. Actually, we can even avoid partitions of unity, but anyway, we need some extra argument to prove the density of the range. Let's also look at discrete analog of this fact. Let's use some notation. Suppose that I is a set and E is a bound space. Let's develop our little C0 of IE, the set of E-valued sequences xi, so formally their functions from I to E, such that they vanish at infinity. Well, it's clear what this means if I is countable, but in the general case, the definition is more or less the same. This means that for every epsilon, we have the norm of xi is less than epsilon for all but finitely many I. So in some sense, this x vanishes at infinity. So this is a vector subspace. Actually, it's a closed vector subspace of the space of all bounded E-valued functions on I. closed subspace. So it is a Banach space for the supremum norm. The norm of x is just the supremum of the norms of xi. So another exercise which is similar to the previous one, construct an isometric isomorphism between the injective tensor product of C0 of I and E and the space C0 with the E-valued C0 space. Okay, now we can answer the question which was discussed in the previous lecture. So let's recall that for each pair of locally convex spaces E and F, we have a canonical map between the tensor product, or exactly from the complete projective tensor product to the complete injective tensor product. This canonical map is uniquely determined on elementary tensors by the following simple formula. So it is the identity map on the algebraic tensor product. And we extend the identity map on the algebraic tensor product by continuity from here to here. This is well defined because it is continued, because the injective tensor, the topology on the injective tensor product is weaker than the topology on the projective tensor product. So at the previous lecture I claimed that in general this map is neither injective nor surjective. And now we can give a concrete example where it is not surjective. An exercise which actually easily follows from the previous exercise. Let's take the tensor product of level 1 and level C0. So what can we say about this map? I find that it is neither topologically injective nor surjective. By the way, it is injective, but it is not topologically injective. And the hint, why is it so? So by the previous results, we may identify this space with the C0 valued level 1 space. And on the other hand, we may identify this space with the L1 valued little C0 space. And they are all the same. This is a hint. Okay, so this is maybe the simplest example which shows that this map is not surjective in general. But in fact, a much more general result holds. So I stated without proof. This fact is more or less an equivalent restatement of the so-called Dvoretsky-Rogers theorem. This equivalent statement of this theorem is due to Grothendieck, and it states that if E is an infinite dimensional Banach space, then the canonical map from the projective tensor product of L1 and E to the injective tensor product of L1 and E.
Если все.
No, an arbitrary infinite dimensional Banach space, not necessarily fixed. This map is neither topologically injective nor surjective. Yeah, for any infinite dimensional Banach space. In the classical form, which is originally due to Dvoretsky-Rogers, this result states that in any infinite dimensional Banach space, there exist summable families which are not absolutely summable. And this is just a restatement of this result in terms of tensor products. Actually, this tensor product is isomorphic to this space of all absolutely summable sequences in E, and this one is isomorphic to the space of all summable sequences in E. We will see soon that that if E is a nuclear locally convex space, then this map will be a topological isomorphism. So the Dvoretzky-Rogers theorem holds because an infinite-dimensional one space is never nuclear. Okay, another useful generalization of proposition 4. Was it proposition 4? So we can extend proposition 4 to locally compact spaces as follows. Proposition 5. Suppose that X and Y are locally compact Hausdorff topological spaces. Then there exists topological isomorphism between the complete injective tensor product of C of X and C of Y and the space of continuous functions on X cross Y. This isomorphism is given by the same old formula. Why is it true? So the idea is to reduce everything to the case of compact spaces. Again, I give you a sketch of proof, but the details can easily be reconstructed. So we choose a pair of compact sets, K1 in X and K2 in Y. Compact sets. And we look at the following diagram. So this map is given by this formula. We define it on the algebraic tensor product, and the definition of the existence of this map on the algebraic tensor product is immediate from the universal property of the algebraic tensor product. And here we equip this algebraic tensor product with the injective tensor topology, and we consider the following diagram. So here we have C of K1 with C of K2. And here we have C of K1 cross K2. The vertical arrows are just the restriction maps. Say R1 tensor R2, so R1, R2, R are just the restriction maps. So we know from proposition 3, sorry, from proposition 4, that this arrow is an isometry with dense range. And I claim that this property of this arrow readily implies that that this arrow, represented by alpha is topologically injective and has dense range. Why is it so? So let's observe that the locally convex topology of the space is given by the semi-norms which come from here. So an arbitrary compact subset in the product is contained in a set of the form of this form. So if we simply induce the semi-norms from here to here and consider all pairs of compact sets, then we get a defining family of semi-norms on here. Similarly, by using the norms here and here, we get a defining family of semi-norms here. So as a result, we see if we use these two families of semi-norms here and here, we see that alpha is in isometry with respect to any of the semi-norms. And so this implies that alpha is topologically injective. The density of the range of alpha follows from the fact that the space is the projective limit of these spaces. The density follows from the fact that this is the projective limit of these spaces. And from a lemma which was discussed some time ago, so when we proved when we discussed the construction of a completion for a locally convex space, we have used the result that a subspace, a vector subspace in the projective limit is dense, provided that it take the canonical projections take this subspace to dense subspaces in here. So since if we look now at this arrow here, so first we go from here to here, and then from here to here, then the composite arrow is easily seen to have a dense range, and so this implies that alpha also has dense range. Okay. By using a single argument, we can prove the following result. This is an exercise for you. You will have a pair of open subsets, U in Rm, and V in Rm, open sets. Then there exists a topological isomorphism between the injective tensor product of the spaces of smooth functions on U and V respectively, and the space of smooth functions on the product, which is given by the same formula. The proof follows the same pattern as in the proof of proposition 5. And again, it turns out, it will turn out shortly that we can actually replace here the injective tensor product by the projective tensor product, because the spaces considered here are nuclear. In fact, it's even now it's rather easy to guess that we can replace the injective by the projective tensor product, because we have already discussed today the spaces of smooth functions of the torus, where the basic tensor product was the projective one. And here we use the injective tensor product, but in fact they are the same for the spaces of smooth functions. And another similar result is about Schwarz spaces. If I take the Schwarz space over Rm and the Schwarz space over Rn, then their complete injective tensor product is isomorphic to the Schwarz space on R and plus n by the same formula. Again, the proof is similar to the proof of proposition 5. And again, it turns out that we can replace here the injective tensor product by the projective one. Okay. Our next goal will be to discuss some functorial properties of our tensor products. Some functorial properties of the projective tensor product and of the injective tensor product. Let's recall, as a motivation, let's recall a well-known fact from linear algebra that the tensor product functor on the category of the algebraic tensor product on the category of vector spaces is exact, in the sense that it takes exact sequences to exact sequences. If we try to extend this to modules over arbitrary ring, then there's another classical fact that the tensor product functor is only right exact on the category of modules, and in particular on the category of abelian groups. So what can you say about the projective and injective tensor products and about their completed versions? So our first goal will be to show that in some sense the projective tensor product is right exact, or more exactly, the projective tensor product preserves co-occurrence. So let's recall some category theoretic definitions. Suppose that A is a category with 0. That is an object which is a terminal object and an initial object at the same time. Let's suppose we have a diagram of the following form in our category, such that psi phi is 0. And let's recall the following definition, which was already discussed some time ago, but in slightly different terms. I claim that Z psi, we say that Z psi is a co-kernel of phi if for every object I have normal letters W. For every W, the following sequence is exact. Home from Z to W, home from Y to W, and home from X to W is exact. So what do I mean by exactness here? So since A is not assumed to be additive, the home sets are not abelian groups in the general case, but they are pointed sets. They are sets with a distinguished base point, and the distinguished base point here is just the 0 map. And for sequences of pointed sets, we may define the notion of exactness in exactly the same way as in the case of abelian groups. Okay, a simple exercise is to understand that this definition is equivalent to our earlier definition of a co-kernel. This is absolutely straightforward. Let's now also recall how co-kernels look like in concrete categories of local economic spaces. And for convenience, let's introduce the following notion. If x and y are local economic spaces, and phi is a continuous linear map from x to y, and we say that phi is strict if it is an open map onto its range. It is an open map of x onto phi of x. In particular, for injective maps, if phi is injective, then it is strict if and only if it is topologically injective. Okay, now let's look at the following exercise. Actually, it is an extended version of an earlier exercise which was discussed when we studied quotients in the category of local economic spaces. So I claim that the pair Z psi is a co-kernel of phi, even only if the following holds. So first of all, let's look at the category of all local economic spaces. And actually the answer will be the same in the category of, well, let's look at the category of all local economic spaces. This is true if and only if the range of psi equals the set theoretic kernel phi, and phi is open. Or equivalently, this can be written as follows. There exists a topological isomorphism between z and the quotient of y modulo phi of x, such that the following diagram commutes. So this arrow is just the quotient map. If we now look at another category of Hausdorff locally convex spaces, then the answer will be slightly different. Or we can also take the category of norm spaces, or the category of Banach spaces, or the category of Fréchet spaces. The answer will be the same. This psi is a co-kernel of phi if and only if the range of psi is dense in the set theoretic kernel of phi, and phi is open. And again, we can write this in the form of a diagram. This is true if and only if there exists a topological isomorphism between z and the quotient of y modulo the closure of the range of phi, such that the following diagram commutes. So the difference is that we must take the closure of the range of phi here. If we now look at the category of complete locally convex spaces, this will be something new. So far, we haven't discussed co-kernels in this category. Or we could equally well take the category of Fréchet spaces or the category of Banach spaces. In all cases, the answer will be the same. So psi is a co-kernel of phi if and only if the range of phi, the range of phi is dense. Oh, we have a little typo here and here.
Mm-hmm.
So first we apply psi and phi. So sorry about that. This is phi of x and this is the kernel of psi. And same here. This is true. Here everything is correct. Here we have psi, here phi and psi. And and again here this is correct. Okay, now. So let's now look at the category of complete locally convex spaces. So psi is a co-kernel of phi if and only if the range of phi is dense in the set theoretic kernel of phi. And psi is a strict map with dense range. And this can also be written in the form of a diagram. There exists a topological isomorphism between z and the completion of the quotient of y modulo the closure of phi of x. So the tilde denotes the completion, such that this diagram commutes. So again, this is slightly different from this diagram, because let's recall that the quotient of a complete locally convex space modulo a closed subspace is not necessarily complete. So we must take the completion here as a result, and this explains why psi is not necessarily open. In fact, it is not necessarily surjective, because this quotient map from x to the completion of the quotient is not necessarily surjective. But it is strict with dense range. Well, let's also look at, for example...
Наверное, тоже надо еще раз фи заменить на пси или... Не, ну фи-то понятно, ну, вроде по определению или нет.
Yeah.
Вот написано and phi is open.
Yeah. Thank you. Psi, of course.
И ниже.
And psi is open, okay. yeah, I had to look always at the original diagram. That's why I interchanged phi and psi. Sorry about that. Okay, well, let's also look at another category which which has metric flavor, namely the category which was denoted by S norm 1. It consists of semi-normed spaces, and the morphisms are linear contractions. Here we have the following characterization. Psi is a co-kernel of phi if and only if, again, phi of x equals the kernel of psi, and psi is a coisometry. It's a coisometry. That is a linear map which takes the open unit ball of y onto the open unit ball of z. And again, we can draw a similar diagram. Actually, we have an isometric isomorphism between these two spaces, such that the diagram commutes. There exists an isometric isomorphism as in A of this form. Okay, so let's now come back to tensor products. So we have the following result. Position. Suppose that A is any of the following categories, either the category of complete locally convex spaces, or the category of Fréchet spaces, or the category of balanced spaces, or the category of balanced spaces and linear contractions. So this band 1 will denote the category of whose objects are balanced spaces, and the morphisms are linear contractions. And suppose that we have a map psi, which is a co-kernel of another map phi in our category. And suppose that, say, y is an object in our category. So I find that the tensor product of phi and the identity map of y is the co-kernel of phi tensor 1 in our category. And a similar result holds for the uncompleted projective tensor product. A similar result holds for the uncompleted projective tensor product and for any A in our standard list of not necessarily complete categories of not necessarily complete locally convex spaces. Well, let's discuss the proof in the case where A is the category of complete locally convex spaces. In fact, essentially the same proof works for other categories in our list. So suppose, let's take our sequence, our diagram. So we have only finite many letters, so let's denote all spaces by x1, x2, and x3. This is phi, this is psi. So we know that psi is the co-kernel of phi. So let's look at the tensor sequence. This is phi tensor 1, this is psi tensor 1. So I want to show that this map is a co-kernel of this map. By the way, if we work, for example, in the category of Banach spaces, then there is a very short and general way of proving this. In fact, in the category of Banach spaces, we have the joint associativity formula, which was discussed some time ago as an exercise. And this formula shows that of tensor product functor, the functor of taking the tensor product by a fixed Banach space Y has a right joint functor, namely a suitable Helm functor. And there is a very simple and general category theoretic fact that if a functor has a right joint, then it commutes with co-limits. And in particular, it commutes with co-kernels. But unfortunately, this simple argument doesn't work for the category, for example, for the category of complete locally convex spaces, because in the setting of complete locally convex spaces, this functor doesn't have a right adjoint. So we have to prove this result directly. But what do we have to prove? We have to prove, let's look again at our definition of a co-kernel. We will prove our result by using a suitable Helm sequence. So we want to prove that for every complete locally convex space Z, the following sequence is exact. We want to show that the sequence is exact. Well, let's try to do it. So, by the universal property of the complete projective tensor product, this space is isomorphic to the space of continuous bilinear maps from X3 cross Y to Z. This is the space of bilinear maps from X2 cross Y to Z. And this is the space of bilinear maps from X1 cross Y to Z. Let's denote this arrow by alpha and this arrow by beta. First of all, let's prove that alpha is injective. Well, indeed, by assumption, the map psi from X2 to X3 has dense range. So psi is a co-kernel phi. In particular, this implies that psi is a strict map with dense range. So psi of X2 is dense in X3. And this readily implies that alpha is injective. Well, because alpha is just the composition with psi, so if some map defined on X3 cross Y will be 0 when composed with psi, that is psi across 1, then the initial map is also 0, because the range of X2 is dense in X3. So the kernel of alpha is trivial. So we have exactness here. Now let's take an element in the kernel of beta, denoted by big F. So we want to show that F actually comes from here. Okay, so let's look at F. So it is in the kernel of beta. This implies that F vanishes. It vanishes on the range of X1 in X2. So F of phi of X, Y is 0. Oh, let me write it in a slightly different way. F of xy is 0 for every x in phi of x1 in the range of little phi. Now let's recall that the range of little phi is dense in the kernel of little psi. Again, because psi is the co-kernel of phi. So by continuity, the same is true for every x in the kernel of psi. Therefore, we can quotient out the kernel, and what we get is a self-theoretic range of psi, and we may define a bilinear map. There is a well-defined bilinear map that's denoted by G0 on the range of psi of x2 cross y to z, such that J0 of J0 of psi, little psi of xy is f of xy. Okay, let's now recall that psi is strict. Psi is an open map onto its range. This easily implies that G0 is actually continuous. Psi is strict. This implies that G0 is continuous. But on the other hand, little psi has that range. So this implies that G0, well, let me write this down explicitly. So on the other hand, psi of x2 is dense in x3. And this implies that G0 uniquely extends to a continuous bilinear map G from x3 cross y to z. And of course, G satisfies the same formula as G0 does. So as a result, we see that G sits here. And this formula applied to G shows that actually alpha of G equals F. So we have started with an arbitrary element F in the kernel of beta, and we have proved that F comes from here. So we see that our sequence is exact. Now this completes the proof. A simple but useful corollary looks as follows. Suppose we have two linear maps, phi1 and phi2, from x1 to x2, or from x1 to y1, and from x2 to y2. I claim that if phi1 and phi2 are open, then so is their uncompleted projective tensor product. If they are strict with dense ranges, then so is the completed projective tensor product. And finally, if our spaces are semi-ordered, xi and yi are semi-ordered spaces, and phi1 and phi2 are co-isometries, then so are their projective tensor products, namely the complete and the uncompleted and the completed projective tensor products. So are this map and this map. To prove this result, we simply observe that our map can be decomposed as the following composition. So we simply apply our proposition to this map and to this map. And so clearly the composition of two open maps is also open, The composition of two maps, strict maps with dense ranges, is a strict map with dense range, and so on. In fact, a little exercise is hidden here, namely, what if our spaces are not complete? Then formally we cannot apply our proposition in case 2. But again, it's easy to see that if we first replace xi and yi by their completions, then this property of our maps is preserved. So if they are strict between x1 and y1 and x2 and y2, then their extensions to the completions will also have the same property. So we may simply apply our previous proposition to the completions of our spaces. And the same holds in case 3. This call explains actually why projective tensor product is called projective. In some sense, in preserved projections, if by projection we mean a projection of the quotient, then the projection of a bound space onto its quotient is an open map. And property 3 states that the projective tensor product of two open maps is open, and the projective tensor product of two coisometries is a coisometry. Okay, so that's all for today. The initial question is, how about the injective tensor product? It's rather easy to show, and this will be discussed at the beginning of the next lecture, that since we have a useful duality between the injective and the projective tensor products, we will see that the injective tensor product preserves topological injective maps, and in some important cases it preserves kernels in our categories. Okay, so that's all for today.
А я что-то потерялась. А в какой момент мы обсуждали, что значит, что